It was very easy for them to be wrong because they were not petroleum geologists in the Norwegian Geological Survey. They were ore geologists. The industry in Norway was very dependent on metal ores. There was no petroleum geologist in the Geological Survey. So in effect, they didn't know what they were talking about. What they should have done was to ask geologists in Denmark, because they're living on a continental shelf, and instead the Norwegian bedrock geologists, they simply extrapolated Norwegian land geology offshore. Had they asked a Danish geologist, they would have extrapolated Danish geology offshore, which was the real situation. So in effect, the Norwegian Parliament, they asked the wrong office.
Exactly. But all the oil that we've found is on the continental shelf.
Yes.
There's nothing on land. Why is that? Why don't we find anything right below us here?
Yes, the answer is there's only one place on mainland Norway where there's sedimentary rocks if you ignore the glacial deposits, glacial moraines. And that's on a small island in the northern part of Lofoten called Andøya. And there are thick sediments of Jurassic Cretaceous, and they're there simply because there was a sedimentary basin there in the Jurassic and Cretaceous, and that survived the erosion from the Ice Age, which happened just recently. So the rest of Scandinavia was scraped clean by the ice, scraped down to the bedrock, which is why usually in Norway you're going on granites and gneisses when you're outside. Well, come here and I'll show you. So here we have the Earth's geological time scale. The entire history of the Earth, 4.6 billion years. That also applies to the entire solar system, the sun, all the planets, comets, asteroids. Everything would have a 4.6 billion year time scale. That's the age of our solar system. The age of the universe is almost 14 billion years. That would go far away over there. The age of our galaxy is 10, but our solar system is 4.6. Now, with the Earth, we find the first fossils about 3.5 billion years. That's about a meter from the end, right about there. 3.5 billion years, the first fossils on Earth. And these are all single-celled microscopic organisms. As we go through time, for almost 3 billion years, there was nothing else. We only find these single-celled microfossils. But here, at this boundary there, what we call the Ediacara age, there we have animals, organisms that you can see without a microscope. So for most of Earth's history, you could only see life with a microscope. Here, starting here, you can see without a microscope. As a matter of fact, the timescale, the Phanerozoic, means visible life. And that was discovered in the 1800s. The geologists already knew that you go back in the sediments, finally you don't see life anymore. So here's visible life, the Phanerozoic.
But what kind of life generated hydrocarbons? How far back do those organisms go?
Well, these organisms were certainly at least partially photosynthesizing cyanobacteria, very simple bacteria, very simple form of life. In effect, you could have had, since you had photosynthesis, you could have had organic rich source rocks far, far back, but all of these rocks are almost all destroyed. For the Norwegian shelf, and the Norwegian petroleum industry, our main source rock, meaning our main sedimentary rock that's rich in microplankton fossils, is late Jurassic, from 145 to 155 million years old. Late Jurassic. That's where most of our oil and gas is coming from. But most of our oil and gas is captured in reservoirs that are Middle Jurassic, is actually older. And they're deltaic sands, river-deposited sand, which cover most of the present-day coast of Norway. Whereas the first sediments in Norway, they are Devonian, about 400 million years old. That means that since the Devonian, the Norwegian shelf has been subsiding. It's subsiding so it can receive more and more sediment. Had it not been subsiding, then it would fill up with sediment and sedimentation would stop. But it's been subsiding, so this is why we say our continental shelf is Devonian in age, and any discovery we make is somewhere between the Devonian and Ice Age sediments. And as it turns out, we have one commercial field that is Devonian age, Embla Field, in the southern part of the Norwegian shelf. And we actually have a field that's Pleistocene, that's glacial deposits, which is absolutely unbelievable. No one expected that. The commercial discovery, the Peon discovery. But most of our resources are Middle Jurassic. We have some Triassic, almost no Permian. We have some shows, some small discoveries, Permian Carboniferous, but most are Middle Jurassic. We have some Late Jurassic, and we have a lot in the Late Cretaceous and some in the Paleogene. So it's all happening here. If you go to the Middle East, then the source rock is much older. But it's the same kind of source rock. It's microplankton-rich source rock, but it's much older. Whereas the reservoirs they have are younger. We have the first deposits from the Devonian, the first deposits on what later became the Norwegian shelf. Since these conglomerates, this gravel, was deposited, the Norwegian shelf has been subsiding, giving room for more and more sediment. So this is erosion from a huge mountain chain that we call the Caledonians. The Caledonian Mountains was pushed up by the collision of Europe and North America. It extended from northern Norway, what is today northern Norway, all the way along the east coast of the United States, where today the Appalachian Mountains are. Part of the Appalachians are remnants of this old mountain chain. It extended through present-day Great Britain, so you still see some of it left in Scotland. Some of the relief in Scotland is from the Caledonian mountain chain. In Norway, it was eroded to flat land. So we have a lot of sediments in Europe and North America from that mountain chain, which would have actually been higher than the Himalayas from the amount of sediment we have and the degree of pressure that it exerted on the continent. And now we're in the sandy Middle Jurassic times. We're having a lot of deposits of older sediments being redeposited by huge river systems on the continental shelf. At this time, you could walk from present-day Norway to present-day Scotland through these lush river deltas. So most of our reserves, about 65, maybe 70% of Norway's petroleum reserves are trapped in this deltaic sandy deposit.
So sand is good because it has these small pores between the grains, so
the small pores.
You can have oil being deposited there.
Exactly.
How big are the pores? How many?
Again, it varies. Generally speaking, in a river-deposited sand, which was the origin of that sand, even though it's an avalanche, river-deposited sand, all the quartz grains are spherical more or less, and they're more or less the same size. So the mathematics show that when you have a stack of spheres that are the same size, it doesn't matter how big they are. it will always be about between 30 and 35% space between the grains. It doesn't matter if it's a stack of grapefruit or oranges stably stacked, there will be about 33% air between the oranges and grapes. Or if they're small marbles, or if they're small shotgun shot, it doesn't matter. It's always the same. Yeah, it's interesting. And that's
so if you have 1 cubic meter of this rock,
yeah.
there will be 30% of this will be able to fill with liquid of any kind.
Exactly. So say like a liter of this rock would give you 3 deciliters of oil if it's oil field filled. So that would be like a big coffee cup. And generally you can extract about 50% of that. So you could extract one.
Why can't you extract everything?
Well, because oil sticks to the sand. It sticks to the sand, and then it requires energy to get it out. It would be similar to a sponge. You can soak a sponge in water, and you can press the water out of it, but you'll never get it all out. It would always be wet. No matter where you're working in the world, if you're working in petroleum geology in a petroleum company, you're either directly or indirectly trying to find porous rock. That's the only thing that can hold liquids, or gas. And porous rocks, as far as Northwest Europe is concerned, most of it is lying in delta deposits. So that's sand that's dumped by rivers as they enter the ocean. So most of our reserves are in this kind of environment. The other environments are beaches, like the Troll gas reservoir, the largest, I think it's still the largest offshore gas reservoir in the world. That's a beach deposit, sands deposited in a landscape like you see here. The first rocks that were explored for were the desert sand dune rocks like you see illustrated here. The oldest, like the Groningen field, was discovered, that was deposited, the reservoir was deposited in that kind of environment. The oldest, geologically oldest field we have, the Embla, is debris from mountains. In this case, an old mountain chain that's been eroded away now. So this is the oldest field we have. Otherwise, we're looking for undersea avalanches. Here's the continental shelf slope, and muddy sands get cleaned up by avalanches. This is very difficult to map, very difficult to find. We have some reservoirs in offshore bars. And of course the chalk reservoirs like Ekofisk and the southern Norwegian sector. So to find those we have to have seismic. So we have to shoot through the sediments to get a picture of the layering of the sediments. And when we have a number of wells through those sediments, we know where these environments occur in the wells. And we can use the seismic to find out where they occur in other places. If the original situation is like plain parallel layers, and say this layer is a clay, we can even say it's a late Jurassic source rock. This is during the time when Northwest Europe was covered by an ocean with anoxic sea bottom. And these are, say, other clays and some sands, maybe some undersea avalanches, maybe delta.
So in the source rock you have small particles that fill up with liquid. Exactly.
Yeah. You have organic remains. This is actually remains of that source rock, late Jurassic. This is the organics of late Jurassic, dissolved from late Jurassic rock, and it's just floating in water. So this is very rich. So when this is heated up, it turns to liquid over time. Now, if this is stretched, of course the continental crust is down deep, say maybe even 6, 7, 8, 10 kilometers. So this is all gneiss and granite, continental rock, basement rock. Now, if this is stretched, then crust tends to break at about 60 degrees. And so that will form a break, and this part, if the stretching is this way, then this part will be thrown down and that will be thrown up. So how does that form a barrier? What happens is that the source rock then is faulted down. Here's the same fault. And this part up here remains high. So actually this goes down, this remains stable in our simplified example here. So here it's cooking at 100 degrees to 130 degrees, or here it's maybe only 80 degrees. So it's not cooking out fluid hydrocarbons from the microplankton debris.
Yeah, because the deeper you go, the hotter it becomes.
The hotter it becomes. Now if it goes down too deep and gets too hot, then this turns to gas. Or any fluids that may have been produced, any oils that may have been produced, will also turn to gas. That's why it has to, to produce oil, it has to remain in that temperature window. Now, a fault is either a pathway for fluid migration, meaning it provides a path of least resistance, because the oil will always want to go up through water, because sediments will always have water in pore spaces.
So if nothing happens here, it'll just leak out.
It'll leak out very slowly, provided if this is a clay also on top, it will go very slowly, and you'll only have light hydrocarbons going first. That takes a long time. If there's a lot of sand, it will go faster, of course, through the sand. There will always be water, so it has to make its way through water. But as soon as there's a fault, then it has a path of least resistance. So it will go up the fault and it will continue. If it reaches, the fault goes to the sea floor, it will leak out in the sea floor. If the fault comes to a sandy reservoir and the conditions are right, topography is right, it will remain the sand. But as a matter of fact, we can make this as sand. No, we make the bottom part of sand. This is actually the real situation. You have the Middle Jurassic sand underneath the Upper Jurassic clay, microplankton-rich clay. So now this sand is up here. Remember I said Norway is unusual that we have our main reservoirs deposited before we have our source rock. But the reason that works is because of this kind of faulting. So whereas this sand is not usable as a reservoir, is down too deep and oil is going up. Where here the same sand is much higher and much colder. So now the oil can go up and it reaches this sand and it's very happy there, so it just goes right in. And it can't go any higher because of the source rock up here, which is just functioning as a barrier, not as a source. Here it's functioning as a source because it's hot. Here it's cold, so it just functions as an impermeable barrier. So that traps the oil in that sand. What doesn't go in the sand just continues up until it reaches another sand or maybe chalk higher up in the late Cretaceous or up to the sea floor. So that's the idea. So this is the same thing. So here we have the late Jurassic source rock, down deep, over 100 degrees. Here we have the same formation here and here. And so this has been faulted down through extension. And so here the source rock is generating oil because of the temperature. Here it's not. A rotary bit. This is what's kind of bit that's used the most. That goes fast, so it's cheap, and it crushes the rock and pumps it up. The drilling mud, this is upside down, of course. The drilling mud flows out of these three holes, lubricates the bit, and transports the crushed rock up, which in this case would be down. So that's
when you take the core sample,
then we use this kind of bit. So here it simply polarizes. It makes a hole this big in this case, but it preserves a cylinder on the inside. And that cylinder, this is a cutaway, this core bit. So the cylinder, as it drills down, it does pulverize a lot of rock. But a cylinder is preserved going all the way up. And once 30 meters has been penetrated, they can penetrate maximum 30 meters, then they have to pull up the whole assembly. And say it's 4 or 5 kilometers below the rig. So you have to pull up, say, 5 kilometers of drill pipe, and the drill pipe is in 30-meter lengths. Here there are 6 meters of core. Today, to drill 1 meter costs, if everything goes all right, there's no technical problems, it costs approximately 300,000 kroner per meter. So it's very expensive to take a core. And even if it was cheap, you wouldn't throw it away, because this is valuable information. This is the most information you know about at this depth, in this case at 2.6 kilometers beneath the sea surface, in this case northern North Sea. Now the reason the MPD keeps all the core, why do we keep this 25% cut? Well, first of all, it's specified in the regulations. Every operating company is responsible for sending a 25% cut of every core from every exploration well drilled on the shelf. That's one of the conditions for operating on the Norwegian shelf. Now, the reason the government wants this sample is for companies who are not a member of this license. They don't have access to that core except through the MPD. All the participating companies on this particular block, they have the rest of that cut. But companies who don't have access to it have access to it through us when the well is 2 years old. Then it's public information. Anybody can come to look at it, and companies can apply for permission to sample it for projects. A company who maybe is interested in a neighboring block. So they want to do studies on older wells to find out about the geology of a neighboring block that they're interested in applying for. So
yeah, because the block that this is from, it's already belong to
yes,
existing companies.
This block belongs to an existing group of companies, and this is a producing commercial reservoir. This is the Statfjord North reservoir. Now, the situation in Norway is because Norway is very expensive to explore in North Sea, Norwegian Sea, Barents Sea conditions. Very expensive. So in order to promote exploration, we subsidize exploration quite extensively. And therefore, we subsidize mistakes. We subsidize dry wells, everything, anything to do with exploration. So we would prefer that the companies drill as few dry wells as possible. If they were paying for everything themselves, we wouldn't care. But in effect, we're paying for most of it. So in order to make them, or to increase, or to lower the risk of drilling dry wells, we provide them with all the raw data they ask for. And that's why geological cores and other types of samples is raw data, oil samples, fluid samples, uninterpreted data. Anything that's not interpreted is public after 2 years. Interpreted, that falls under a different law, which is called the Intellectual Copyright Act. That's a 20-year release date.
So by giving other companies this information, you make sure that they don't drill more dry holes than the most necessary, and it saves money for the Norwegian state.
Exactly. The fewer dry holes, the more money saved. So exploration subsidized, production taxed. That's the idea. And that lowers the risk for the companies, even though it also lowers their profits because they pay higher tax on production, but they pay much lower cost for exploration. And apparently it works out because we have a lot of companies on the shelf.
Sounds like a good idea.
Can you show the difference between a dry well and a
Yeah.
with an oil find?
This is a gas discovery, if I remember right. It's not
Can you smell it?
You can't really smell the gas, but if it was oil, you could smell it.
Well, what is the difference if it's? What is the difference in smell if it's gas or oil?
Well, no, gas you can't smell.
Okay.
Yeah. Which is mainly methane.
But oil
in
you
oil,
can,
oil smells like diesel.
Okay.
It sort of reminds me of an automobile garage.
You need some help?
I think.
Okay.
Okay, here we go. So this is ecophyst that's been glued in place with epoxy. So this can't be sampled. It's, as I mentioned earlier, sometimes.
Is it too old to smell still? Has it
I think so.
evaporated everything?
Yeah, you know, the epoxy smells itself. Oh, this is the glued stuff. I'll try to find some that are not glued.
What is the point of gluing them?
Well, especially in before, Well, even today, all cores are glued through the center, full diameter. A small section is cut out, about a centimeter thick, and is glued. It's only used for visually, for describing the sedimentology. Then above and below that, then it's used for sampling, for doing studies. And that's why what's called the resin cut, because of this epoxy resin, is preserved. And also it's not to be used except for visual use for them. So that's Ekofisk, and it's in the oil zone, so it's brown stained. In the water zone, it's totally white, like chalk, because I mean that's what it is. So the rest of the well is just pumped up in the drilling mud. It's crushed through a rotary drill bit that just crushes the sedimentary rock, and then it's circulated up through the drilling fluid, which cools the bit and also removes the crushed rock, so it doesn't plug up. And this is what it looks like. So we receive 1 kilo of this, 1 kilo dry weight of this crushed rock. Now it's still usable, especially for microfossils, for organic content. Geochemistry, it's still very useful, but it's not usable for calculating porosity or permeability, meaning how easily do fluids flow through it, how much space is there between the grains. It can't be used so much for that. Only a core can give that information. So, but it's still the only thing we have, so it's very valuable material. Now, the sample I just showed you is called cuttings samples. That's the crushed rock that the rotary bit produces when it drills through sedimentary rock. So we receive 1 kilo of this crushed rock every 3 meters in a well, 3 to 5 meters, it varies. So most of a well is represented by the crushed rock. In addition to that kilo, the regulations specify that the operator must also send a duplicate of that crushed cutting sample, a duplicate sample that is washed. The drilling mud is washed out of it. The original sample I showed you, the drilling mud is in place. So here it's washed out, so you see the actual sedimentary rock. Now what's special about this set of duplicates is that they are never to be used. They are never to be released, only looked at. And the idea was that in the future, when oil and gas is history, we'll still have this archive of geology of the Norwegian shelf, because we don't know what technology and science will bring us in the future. This may be extremely important for something that we can't even dream of today. And it's very cheap to keep it. But if we were to use it up, it would be very expensive in 500 years to get it back, when no one knows how to drill a well anymore. So that's why we keep it. And probably nothing will ever come of it, as far as, except for pure geological study, paleontology and others, of course. We can easily see that. But as far as something that we don't know about yet, maybe, probably nothing will happen, but it's good to have it just in case. So this is never to be touched. This is for posterity, for our great-great-grandchildren's great-great-great-grandchildren.
It's exactly the same way we think about keeping archives. We don't really know what it's going to be used for, but it has some potential, obviously.
Exactly.
And it's cheap to keep.
It's cheap to keep.
And if you throw it away, well, it's gone.
It's gone.
So it's a perfect archival thought.